Welcome to today's GATE section. I am Pradeepa, Assistant Professor, EEE Department of S.A.E. Engineering College. Today I am going to present the topic of parallel operation of alternators. This is the GATE syllabus for electrical machines, and I am going to take the topic of parallel operation of generators or parallel operation of alternators. Now let's see what is parallel operation of alternators. Parallel operation of alternators is connecting one alternator in parallel with another alternator or with an infinite bus bar is known as synchronization or parallel operation of alternators. Here we are using two alternators. The alternator which is already carrying the load is known as the running alternator, and the alternator which is connected in parallel with the system is called the incoming alternator. Why we are going for parallel operation? First one is load sharing and capacity. It allows multiple alternators collectively meet the total demand which might exceed a single unit's capacity. Next is reliability and continuity. If one alternator fails, the other alternator can continue its operation so that we can get uninterrupted power supply. Next is maintenance and flexibility. When one alternator is shut down for maintenance, the other alternator can run at its full load demand. Next is efficiency. It enables operating the alternators at their optimal, most efficient condition. This is the diagrammatic representation of parallel operation of alternators. This is the incoming alternator, alternator 1, and this is the alternator 2. Here the two alternators are connected to the bus bar which is connected to the load. This is the synchronizing switch. Alternator 1 is the running, that is the outgoing alternator, and alternator 2 is the incoming alternator. We can also address it as machine or generators. These are the reasons for parallel operation for alternators. First one is continuity of service. When many alternators are connected, when one alternator is shut down for inspection or for maintenance, the other alternators can continue its for continuity of the supply. Next is efficiency. During the periods of light load or one or more alternators may be shut down, and those operate at full load, and hence more efficient condition can be received. Next, when several alternators are operating in parallel, can supply a bigger load than a single alternator. If there is a breakdown of an alternator, there is no interruption of the power supply. Next is load growth. In order to meet the increasing future demand of the load, more alternators can be added without disturbing the original installation of the power system. Next is economy. The operating cost and the cost of the energy generated are decreased when several alternators operates in parallel. These are the conditions for parallel operation of alternators or generators. First one is voltage equalization. Next is frequency synchronization. Next is phase sequence and phase angle. The last one is phase angle. Voltage equalization. In voltage equalization, the terminal voltage of the incoming alternator must be equal to the voltage of the bus bar. In frequency synchronization, the frequency of the incoming alternator's voltage must be the same as the outgoing alternator or the bus bar frequency. Next is phase sequence. The phase sequence of the incoming machine must match the phase sequence of the outgoing machine or the bus bar. Next is phase angle. The voltage of the incoming machine must be in phase with the bus bar voltage. So these are the conditions which will be satisfied for the parallel operation for alternators or generators. Next is methods of alternators synchronization. There are two methods, lamp method and synchroscope method. In lamp method there are three types. First one is three dark lamp methods, three bright lamp methods, two bright and one dark method, and synchronoscope method. How it works? This is the procedure for both synchronoscope method and lamp method. First one is matching, next is synchronization, next is connection and load adjustment. Matching, that is the incoming alternator is brought up to the speed and its voltage is adjusted to match the bus bar voltage or the outgoing alternator. Next is synchronization. The frequencies are matched and the phase angles aligned to ensure that they are in equal. Next is connection. Once synchronized, a switch is closed connecting the alternator to the common bus bar. Next is load adjustment. The load is shared, that is with the active power controlled by the alternator's shaft input and the reactive power controlled by its excitation. So this is the procedure for both synchroscope method and lamp method. Okay, this is the diagrammatic representation of for lamp method. This is the incoming alternator and this is the outgoing alternator. Two alternators are connected to a common bus bar. This is the main switch which is connected to the outgoing alternator. This is the synchronizing switch. These switches are called the synchronizing switch, and these are the lamps. Okay, that is lamp. Lamp 1 is connected between the R phase of the incoming alternator and the bus bar, and lamp 2 is connected between the Y phase of the incoming alternator and the Y phase of the bus bar, and the lamp 3 is connected between the B phase of the incoming alternator and the B phase of the bus bar, and your voltmeter is connected between the R and Y phase of the alternator 2 and R and Y phase of the bus bar. Okay, the voltage, this voltmeter is connected to check for voltage matching between the bus bar and the incoming alternator. So this is the diagrammatic representation of the lamp method. Okay, so there are 3 types in lamp method. First one is 3 dark lamp method, second one is 2 bright and 1 dark method, the third one is 3 bright lamp method. Okay, in 3 dark lamp methods, all the 3 lamps should be simultaneously go to dark, must be in dark, indicating perfect synchronization and equal voltage and phase. Only if the 3 dark lamps simultaneously they go to dark, only it is indicated that they are synchronized for perfect voltage and phase. That is, both the voltage of the existing alternator and the bus bar should be same, and the phase of the alternator and the bus bar should be same. Only at that time the lamp will go to dark. Next is 2 bright and 1 dark method. In this type, 2 lamps will glow bright simultaneously and 1 lamp will go to dark when there is a perfect synchronization between voltage and phase. Next is 3 bright lamp methods. In 3 bright lamp methods, all the 3 lamps will glow bright simultaneously, indicating perfect synchronization between voltage and phase of the alternator and the bus bar voltage. Okay, when all these three conditions are satisfied, the synchronizing switch is closed, and at the exact moment the conditions are met. Now this is the diagrammatic representation of synchroscope method. Okay, in synchroscope method, same 2 alternators are connected, that is the incoming alternator and the outgoing alternator, and this is the main switch is connected to the outgoing alternator, and synchronizing switch is connected to the incoming alternator, and same a voltmeter 1 and voltmeter 2 is connected between the R and the Y phase of incoming alternator, and the voltmeter is 1 is connected between the R and Y phase of the bus bar, and here a synchronoscope is connected to determine the equal voltage and phase of the alternators. Okay, in synchronoscope method, the pointer's direction indicates whether the incoming alternator is running faster or slower than the bus bar's frequency. Once the pointer is stationary, the synchronizing switch is closed. Okay, when the synchronoscope, that is here, this synchronoscope's pointer, this will indicate whether the alternator is running slow or fast, and at that time we can close the switch. Okay, this is the load sharing by 2 alternators in parallel operation. Okay, this is the alternator 1 and alternator 2 frequency and load. Okay, we'll see this derivation. F1 NL is the no load, it indicates the no load frequency of alternator 1. F2 of NL indicates the no load frequency of alternate 2. This is F1 is the full load frequency of alternator 1. F2 is the full load frequency of alternator 2. F is the common frequency when the 2 alternators are operating in parallel. Okay, W1 is the full load power rating of alternator 1. W2 is the full load power rating of alternator 2. P1 is the power shared by the alternator 1. P2 is the power shared by the alternator 2. P is the total power delivered by the 2 alternators. For alternator 1, the drop in frequency from no load to full load is F1 of NL minus F1 of FL, because NL indicates no load and FL indicates full load. Drop in frequency per unit power rating is equals to F1 of NL minus F1 of FL divided by W1. Drop in frequency for the load of power P1 is equals to F1 of no load minus F1 of full load divided by W1 into P1. Therefore, the operating frequency of the alternator 1 would be F1, that is no load frequency minus drop in frequency. Okay, here the formula is for F1 of no load frequency, the drop in frequency is F1 of NL minus F1 of FL divided by W1 into P1. Okay, this is for alternator 2. Your drop in frequency for alternator 2 from no load to full load is F2 NL minus F2 FL. Same, NL is for no load, F is for full load. Drop in frequency per unit power rating is equals to F2 NL minus F2 FL divided by W2. Here the drop in frequency of load of power P2 is equals to F2 NL minus F2 FL divided by W2 into P2. Therefore, the operating frequency of alternator 2 would be F2 is equals to no load frequency minus drop in frequency. F2 is equals to F2 of NL minus F2 NL minus F2 FL divided by W2 into P2. Next is for parallel operation, both the alternators must operate at the same frequency. Thus, from equations 2 and 4, we have, that is equation 2. This is the equation 2. This is the equation 4. By equating equations 2 and 4, we will get the final equation. That is, the total F is equals to F2 of no load minus F2 of no load minus F2 of full load divided by W2 into P2, and the total power delivered by the two alternators will be sum of the two alternators, that is total P is equals to P1 plus P2. Okay, this is the derivation, and these are the important formulas which we will be using for our solving a gate problem. Okay, now let's see a solved gate question. Okay, the question is, two station alternators, that is alternator A and alternator B, operate in parallel. The station capacity of A is 30 megawatts and that of B is 60 megawatts. The full load speed regulation of station A is 4% and the full load speed regulation of B is 4.5%. Calculate the load sharing if the connected load is 60 megawatts and no load frequency is 50 hertz. Okay, let's see the solution. Now let the load shared by alternator A in M megawatts will be PA. Let PB be the load shared by the alternator B. So PA is the load shared by alternator A and PB is the load shared by alternator B. Okay. Now when we sum of PA plus PB is equals to 60 megawatts. Okay. Now the original frequency of the system at no load is, that is F of NL is equals to 50 hertz. That's given in the question. Okay, now we will first calculate for alternator A. For load of 30 megawatts, the drop in frequency is equals to 4% of frequency of no load frequency. That is 4 by 100 into 50. That will be equal to 2 hertz. Now for the load of 1 megawatts, the drop in frequency is equals to 2 by 30, which is equals to 0.067 hertz. For a load of PA, that is for alternator 1, the drop in frequency is equals to 2 by 30 into PA, that is equals to 0.067 PA hertz. Hence, the operating frequency of the alternator A is FA is equals to FNL minus drop in frequency. FA is equals to 50 minus 0.067 PA. This is for alternator B. Similarly, the operating frequency of the alternator B is given by FB is equals to FNL minus drop in frequency. FB is equals to 50 minus 4.5 into 50 into PB by 100. So by equating we will get FB is equals to 50 minus 0.0375 PB. For parallel operation, both the alternators must operate at the same frequency. So that is the frequency of alternator A will be equal to the frequency of the alternator B. We saw in condition satisfying parallel operation of alternators, that is both the alternator frequency should be same. Okay, from that we are equating. So frequency of alternator A, that is equals to 50 minus 0.067 PA is equals to, that is, now we'll equate for FB, that is equals to here this FB, 50 minus 0.0375 PB. Equating the both FA and FB, we will get the value for PA, that is 75 divided by 134 PB. Okay, now PB, for equating PB, we'll get 134 by 75 into PA. We're equating fourth and fifth equation. Okay, by solving this, we will get PA is equals to 60 minus 38.71, which is equals to 21.29 megawatts. Okay, so we have found out the value for the alternator A and alternator B. So this will be the final solution. Okay. By concluding, that is, we have seen that parallel operation of alternators involves connecting two alternators in parallel to a common bus bar to share the load so that it can enhance the reliability and improve the efficiency of the system. Thank you. We will continue the gate video for the next section.